Hi students, today we're going to look at average value and we are also going to introduce something called the fundamental theorem of calculus. It's pretty important, in fact you might call it fundamental, and specifically about how to evaluate integrals, connecting them to something else that we know something about. Alright, so we've got some graphing stuff. This looks like everything that we've been doing and loving to do for the last few days. And here we're looking at some areas here. Okay, so this is the area from 0 to 2. Here's 0, here's 2. That's a quarter circle with radius 2. So I'm going to say area of circle is going to be pi times 2 squared, so 4 pi. And for a quarter circle, that would be 1 pi. Only one thing is tricky. This is below the x-axis. So this has got to be negative pi. I'm going to erase my equals just so that that is very clearly negative pi. All right, going from 2 to 6. So here's 2, here's 6. This is this area. Triangle, we've got a width of 4, height of 2. That has an area of 4. All right, third one, going from negative 4 to 2. 1, 2, 3, 4. Here we've got 2 by 1, so that's going to be negative 1 as an area. Here we've got a negative pi, just like the other one. And going up to 2, we've got another negative pi. This would be negative 2 pi minus 1. All right, going from negative 4 to 6, that's the whole shebang. I'm going to take what I had here for negative 2 pi minus 1. And I'm going to add the last triangle on here, so that's plus 4. So that'd be negative 2 pi plus 3. All right, number 5, we're doing the same thing, but we're doing the absolute value of the function. This is going to be really tricky because what this means is that we are taking the area of each piece and making it positive before we add them together. So we'd have 1 plus pi plus 4. So 5 plus 2 pi. We have to be a little bit careful. If this had been the absolute value on the outside of the integral, with the answer we got here, we would have taken the absolute value of and given us about positive 3 as an answer. Okay. Then we're looking at what happens if we shift this whole graph up by 2. I'm just going to move my axis down, and I'm going to go kind of piece by piece here. So we're adding 8 to this, and we already said the triangle part was 4. Here we've got a 2 by 4 box that then we're subtracting this semicircle from. So I'm going to call this 8 minus 2 pi to get this part down below. It's a little bit awkward. And then here we've got, I guess this is a trapezoid, or I can think about this as a 2 by 2 square that I'm minusing this triangle out of. I like that. So I'm going to call this 4 and then minus 1 for the triangle. Okay, 4 minus 1 is 3, plus 8 minus 2 pi, and then plus 4 plus 8 is 12. 23 minus 2 pi seems to be my... Okay, so let's talk about average value. I like to think about average value as, and if we were in person dealing with finding the average amount of M&Ms. So if I covered this whole thing with M&Ms, and then if I had bars on the sides and started to squish this down, somewhere I'd be able to make a rectangle with those M&Ms. They'd all squish to make a rectangle of some height. We may know some stuff about this because of this specific shape. So if we've got an isosceles triangle here, would it make sense that the M&Ms that would fill this triangle, if I wanted to just have them squished down into the rectangle would fit exactly here. It's almost like we took a piece of this triangle and we put that there, and we took a piece of this triangle and we put that here. We're going to have a general way to think about this. But if we think about the area of this triangle, so let's call this the integral, in this specific case is going to be from 0 to 6. But let's generalize that and go from A to B. There's my function, f of x, and that would be the triangle. This would be that area. If I wanted to see what the average height was, it's like we're saying that this is equal to some kind of base times a height, and that would make a rectangle. I want to know what the height is, so let's make that the height, and we're going to divide by the base. We make that a capital B so we don't have two lowercase b's in this problem. We've got the integral from A to B, f of x dx, and then divide this by that base. And one thing I'd like you to know is that, and Groot would like you to know as well, is that we're going from B to A, so my base is actually going to be B minus A, the length of that interval. What's really neat about this is that this gives us the average value of this function. And we're going to learn some stuff today. It's going to let us write things a little bit differently. And we're going to see this connect back to things that we've been using for a very, very long time. But for now, this is defined as the average value. The total area divided by the width of that interval. Okay. Thing number two, we've got a whole bunch of stuff going on here. I'm going to identify some of these things, and what I'm going to say is that this blue graph has something to do with some of the other things that are happening here. I'd like you to take a few minutes, see if you can take a look at all of the different things that are going on here, and see if you can make some sense that connects the blue graph to the green graph to maybe this gray area and maybe some of the values that are going on here. Please pause and try to make some sense of this. All right, thanks for playing along with the pausing part. Here's some of the stuff that I notice when I look at this. I notice these two equations are related. I notice that the green equation is the derivative of the blue equation. So if I call this f of x, if I take the derivative of x squared plus 3x, I get 2x plus 3. This would be f prime of x. That's kind of cool. All right. The second thing that I'd like you to notice, or the second thing that is important for us to notice, is that these points, so going at 540 and 11,154, are connected to this stuff down here. So if we think about this in terms of this integration, so if we have the integral from 5 to 11 of what we now call f prime of x, does it make sense, and I forgot my dx, bad on me, but I fixed it, that this would be this area under this curve? I hope so. The second piece to go with this is that that's connected to some things here. And that's kind of weird because I've got these two numbers, 40 and 154, that just happen to be 114 apart. So if I were to say we're talking about f of 11 minus f of 5, that would also be 114. Using either substitution or the transitive property, we can make a kind of weird statement that the integral from 5 to 11 of f prime of x dx is equal to f of 11 minus f of 5. Okay, let's generalize this a little bit and say something like, I'm going to change colors, the integral from a to b of some derivative is equal to whatever that function is the derivative of at b minus f of a. This is a really, really big deal. This is something called the fundamental theorem of calculus. We often talk about the fundamental theorem of calculus in two parts. Books like arguing about which is part 1 and part 2. Doesn't really matter so much to me as long as we kind of understand what's going on here. So I'm going to talk about this as FTC, and I'm going to introduce a little bit of notation for us, where we have the integral of a function from a to b. I almost forgot my dx again. And instead of going from f prime to f, we're going to go from the function to a capital F. But this means exactly the same thing. So big F of b minus big F of a. And I could treat this in terms of derivatives, and then we'd be looking at from a to b, f prime of x dx is equal to f of b minus f of a. Both of these mean exactly the same thing, expressed in slightly different ways, and either one is okay. Okay, so we're told that f is the function of accumulation going from 0 to x. You have to switch variables if we use x, because if we're plugging in x for x, it's just kind of weird. And we want to find all of these things. So let's find these things. So f of 0, that would be going from 0 to 0, so that would have an area of 0. F of 1, that would have an area of 1/2. F of 2, that would have an area of 2. F of 3, okay, so that's 3 squared, so that's 9 over 2. F of 4, that's going to be 4 squared over 2. You might notice I'm writing things kind of funny. F of 5, we might suspect is going to be 5 squared over 2. F of 6 is going to give us 6 squared over 2. And if we had some unknown number f of a, that would be a squared over 2. And since we have this function 2t, that gives us some actual values here. I also realized that I did not actually use that function and totally ignored the numbers on the left side because for me they're under my markers. So I have to double all of these things. So that would be 1, 4, 2 times 9 over 2, 2 times 4 squared over 2, 2 times, and 2 times. So we're saying that the integral of 2t going from 0 to x is basically equal to x squared. Which again is kind of weird because I know that the derivative of x squared gives us 2x. And this process from 2t gave us back that x squared. That's kind of a weird thing. All right. So this weird thing that we're kind of hovering around connects integrals, the areas under curves, and derivatives, which is really weird, and gives us this idea that these things are connected. So again, I'm going to write the general form of this, and we're going from a to b of some function f of x dx, and that's equal to what we're going to call the antiderivative of f evaluated at b and a and subtracted. In terms of derivatives, if I want to write this in that way, and again, that's totally fine, we've got the integral, so the area under the curve from a to b of some derivative, is going to be equal to that function evaluated at b minus that function evaluated at a. And that's the first thing that we have that connects this new idea of area under curves to derivatives.